Hello everyone and welcome to Chapter 2. Chapter 2 is all about modeling distributions of data. Section 2.1 we're going to talk about where data elements are in relation to the whole set of data. And in Section 2.2 we're going to talk about the normal distribution and things related to that topic. It's a very quick chapter. We should finish this chapter in about 7 days or so. So hold on to your hats, stay tuned, make sure you're paying attention. We're going to go fast. Okay, here are the learning objectives for Section 2.1. You may want to pause the video and read through them. I am not going to read through them individually. We're going to go through each one at a time. So for today, we're going to talk about the first 3. All right, percentiles. One way to describe the location of where a data element sits in relation to the whole set of data is the percentile. One of 2. We're going to look at 2 different ways today. So the percentile, most of you are familiar with this concept. Every time you take a standardized test, you get back a score that says you are at the X percentile or the P percentile in this case. The percentile tells you where you are and how many data elements or what percent of the data elements are less than your score. So that's how that works. All right, so here's an example. Suppose that Jenny earned a score of 86 on a test. We want to know how did she perform relative to the rest of the class. The score of 86 in and of itself doesn't really tell us very much about Jenny and how well she did, because maybe everyone else in the class did better than she did. Maybe they did worse. We don't really know. Looking at this STEM plot, we can actually see that she did pretty well compared to the rest of her class. Her score of 86 right here is well above the mean, we can see, and well above the median. So, how did she do, in fact? Her score was greater than 21 of the 25 observations. So the observations that are in red, those are the scores that were lower than Jenny's. Since 21 of the 25, or 84% of the scores, are below hers, Jenny is at, not in, but at the 84th percentile in the class scores distribution. Okay, when you're talking about percentiles, things we want to consider are the following. We want to talk about, what about the person with the highest score? How does that work? Suppose you have 10 people in your group and somebody is at the top of the list, then 9 out of 10 scored less. So that person would be at the 90th percentile, even though they scored the highest score. Some sources include the data element, but we are not going to include it. Our book, and I believe this course actually accepts the data either way, so that it doesn't really matter. But in our book, we exclude the P data value, the P, okay, sort of like the X data value. Okay, when 2 or more data values are the same, they will be at the same percentile, all right? You calculate the score by excluding both or all values that are the same, okay? Percentiles should be expressed as whole numbers, rounded to the nearest percent. And based on the example that I gave at the beginning of this slide, percentiles are more meaningful with larger data sets, right? So that you can have a 99th percentile. Okay, so here we go. Relative. Topic number 2 in this section is a cumulative relative frequency graph. Big words, lots of words. So we're going to look at each one. Cumulative means add up all the numbers that come before. Relative means turn your numbers into percents. Frequency means we're counting how many data elements fall within some interval. And we're going to put it all onto a graph. All right, so that's what that's all about. Let's take a look at some data. So here we have a chart. This is actual data, the age of the first 44 presidents of the United States at the time when they were inaugurated, rounded to the nearest year. So we have 2 presidents between 40 and 44. I don't know if anyone knows who they are. The answers would be Teddy Roosevelt and John F. Kennedy, Teddy being the youngest. And all the way up to the oldest, which would be, we have in the oldest category Ronald Reagan and then a few others. All right, so there's our data, and those are frequencies, how many. All right, so now relative frequency, we've seen this before in Chapter 1. We take the frequency and divide it by the total number of data values, in this case 44, gives us our percents. Next, we find the cumulative frequency. Cumulative frequency is found by adding. So we have this number 9 here, which comes from adding 2 and 7. Then we have 22, which is 2, 7, and 13. And so on, all the way to the end. Notice that at the end it adds up to 44, which is all of our data elements. Next, we're going to calculate the cumulative relative frequency by turning this column, the cumulative frequency column, into percents. So we divide by 44, that gives us our percents. Notice that at the end we add up to 100%. And then we put it on a graph. Notice this is a line graph, and it has a few things that are of interest. Number one, it starts at 0 and at 40, 40 being the lower end of the smallest data bucket, okay? And then it goes, the next data point is 45, which is the first number in the next bucket, and so on. So 45, and then 50, 55, and so on. And the percents, we put in the percent. Okay. Another name for relative frequency graphs is ogives. I don't know that that's on the test, but just FYI. This slide has a typo. That's why the first bullet point is crossed out, because it's there twice. So calculating, we've already gone through this. These are the same things that I just said, how to make a graph. You can write this down if you'd like to, or read through it and make sure you understand the steps. Okay, a couple things to consider, and I've already talked about this as well. The points on the graph correspond to the relative frequency in each class at the smallest value of the next class. Okay, you start at 0 and the smallest value of the first class, and you end at 100 and the greatest value of the last class. Okay, so there's our data. The last topic that we're going to cover in this video is a z-score. A z-score tells us how many standard deviations from the mean an observation falls and in what direction. So it's another way of telling us where within the distribution a data element lies. So in this case, it acts as an observation from a distribution, and the distribution has a known mean and a standard deviation. Then the z-score, also known as the standardized score, is calculated as follows. Z is equal to the difference between the data value and the mean. Notice it's x minus the mean, divided by the standard deviation. That just tells you how many standard deviations away from the mean. It is a signed number. The z-score can either be positive or negative. Z-scores that are greater than the mean would be positive, and z-scores that are less than the mean would be negative. So let's see if this example is going to work here. Okay, so Jenny earned a score of 86 on her test. The class mean was 80 and the standard deviation is 6.07. Think about her standardized score, her z-score. Do you think it's going to be positive or negative? What is it going to look like? So think about that in your mind for just a second, and then we're going to go on. All right, so here's our formula. We take x minus the mean, so 86 minus 80, divided by 6.07. 86 minus 80 is 6, so we're just about at 1. What does that mean? That means that Jenny's score is 1 standard deviation above the mean. And that is the end of this section. I did put a picture in here of my dog because I thought you might like to see him, but it's not a very good picture. It's hard to see. But here's my little dog Tucker holding his favorite toy, a stuffed elephant. I hope you enjoyed this video.